we are going to get started, still on chapter 8, but we're moving on to hypothesis testing for a single mean. This is not part of your homework for this coming cycle, so it won't be in your online test. And we won't get it finished today, I know that, because I've got other things that we'll be doing. But at least I'll give you a head start, and when we come in Monday next week, we'll continue and finish this section off. So hypothesis testing is kind of halfway through. We've looked at a single proportion hypothesis testing. We've also looked at a difference between two proportions hypothesis test. So what's left? We're going to do hypothesis testing where you look at is there evidence for a single mean, and is there evidence that it's bigger, less, or not equal to some fixed value. And then lastly, we'll be doing comparing two populations. So let's give you a little bit of background on how these ones differ in a number of ways from single proportions, and in other ways are very similar. So we're going to just have one we're going to have one population. And let's say that in this population, we believed that the mean used to be, let's say, 100. So let's say it's the IQ of Scotsmen. In the past, the IQ of Scottish people had a mean of 100, right? That's going to be the guy we're going to compare it against. But we think now that Scottish people have got more intelligent. Can't think of a reason why they would think that, but they think it's true. And so what we're going to do is a hypothesis test where we are going to see if there's evidence to prove that. So you typically do the usual thing. You go out and you get a really good random sample that's unbiased and a good representation of the population. And there was 200 people in this random sample, and the mean IQ was 101, and the standard deviation of the sample was 10. Now, if we look at it superficially, there is some evidence that the IQ has increased. Agreed? It's bigger, right? Used to be 100. This sample has said it's maybe a little bit bigger. And that's what we're trying to see. Is there enough evidence to prove that Scottish people have increased their IQ, since 20 years ago? So how are we going to do this test? Well, the theory behind it is that the sampling distribution, that's where you collect samples of size 200 and you do lots of them, right? You get a sampling distribution. If this was true, it would be at the 100 mark, and there would be a certain standard deviation for it called the standard error, and you could actually calculate the standard error. That's its formula. And in this case, you would get, what would you get? You'd get 10 over the square root 200. What would that look like? It's about 0.7. And so if you were going to look at all the samples that you could get from this population, and you chose a sample of size 200, if the population was still 100, this is what you would get. You'd get a 0.7, so that'd be 100.7, and then you'd get 101.4, and then you'd get 102.1. Now we've got a sample mean that's 101, which is roughly about here, right? We are going to find that area there. That area there essentially represents the probability that you could get a sample bigger than or equal to 101. And that green area is what the p-value that we've been calculating all week is. And the logic says this: if that value, right, that p-value is really, really small, then isn't that evidence that it's not 100 anymore, it's bigger? That's kind of the way the logic goes. So p-values have to be small, and the way that we decide what does small mean, it has to be less than the significance figure alpha. So let's say in this particular question that we wanted to test, has the IQ of Scottish people got bigger? And we're going to use a significance level of only 0.1. So that's like the easiest hurdle to beat. So what we're going to do is we are going to calculate essentially the p-value. And we're going to do that by using using software. Now you can do it by hand, well, partially by hand. If you wanted to, you could take your data, you could find its z-score. You can then find what's the probability that your z-score is bigger than some number, and off you go and do what you need to do. But it's a bit cumbersome, and it's much easier to do it using software. But before we go, I want to tell you about a guy called Degrees of Freedom, very often DF for short. The degrees of freedom is the sample size takeaway 1. So in my case here, it's 200 takeaway 1. The degrees of freedom are 199. So if you get a question and I ask you, what is the degrees of freedom? My degrees of freedom, simply it's just the sample size takeaway 1. This particular distribution that we're using looks like the normal distribution, but we're actually going to be doing what's called the T distribution, the student T, if you want its full title. And that was the guy who worked for Guinness who came up with this. And it's a way of dealing with data that may not be particularly normal in shape. So if your data is a little bit, your population is skewed left or skewed right or got something wrong with it, the student T distribution copes with that. And this little degrees of freedom is just part of that process. So I'm going to try and make that happen. And here goes. Where are we? Click on it. Go basic. I've lost you. Okay. Space. You can never find things when you want them. Okay, my mic just went away on me. Can you hear me? Okay. I also lost my the file. So if you wait a few moments while I reload it, for some reason it get closed. I don't know why. Okay. So in my story, oh come on. God, this has been a pain today. You ever get one of those days when nothing wants to cooperate? I'm having one of those days. Yeah, I know what it's like, Mackenzie. I'm having technical difficulties right now. There. Are we finally looking at salt? So what you see on the screen in front of you. Okay, so what we're testing here is the population of Scotland bigger than 100? That's what we're going to be testing. And so we're going to go inferential statistics, a one sample T, You're going to do the mean of that sample, which in our case was what, 101. The standard deviation of the sample was 10. The sample size was 200, right? So that's where those numbers go. Then we scroll down to the hypothesis test, and the population used to be an average of 100, and we're trying to see, is it greater than? So that's where that was. And now we generate the results, and there is your p-value. Do you see it at the end, 0.079? So our p-value is 0.079 and some stuff. Now, there are some other data points here that you can be asked. For instance, isn't there a guy very often where they ask you for the test statistic? You remember those questions? Test statistic. In this world, it's the T statistic. It used to be the Z when you did proportion, but when you do means, it's typically the T statistic. They might ask you for the degrees of freedom. Do you see that 199 that I mentioned? So pretty much everything and some stuff you probably don't need to know is here. Can you see our null and alternate hypothesis, the way they should be written? Everything is here. So p-value is the most important one, and it's this guy. So let me now return and see what we have. Is our p-value less than the significance level alpha? Just like we did with the proportions. Is 0.079 less than 0.10? In this case, the answer is yes. We agree that's less than that. And when it's a yes, you have various sentences that you use. I'll try to find their particular one that they want to use here. And the sentence would look something like this. At the alpha equals 0.1 level, we reject the null hypothesis. And conclude that the data is statistically significant. So that's going to be your go-to sentence when they talk about you've found your p-value, you've done your test, the answer is yes, right? This is less than that. When it is less, you've got the evidence you're looking for. So they give you like 4 sentences, but this is the one that would be representing the situation. So at alpha equals 0.10 level, we reject the null hypothesis and conclude that the data is statistically significant. If, however, you do the same test, but the answer is no, your sentence will look very similar, but with differences as well. At the alpha equals 0.10 level, we fail to reject the null hypothesis. Do you see that extra word? Fail to reject. And then the rest of that sentence will have something like a comma. And what do we conclude? And conclude that the data is not statistically significant. And you see an extra word, not statistically significant. So there'll be 4 choices, but that's the choice if you get a yes, and that's a choice if you get a no. And the other choices are never going to work. So you don't even need to pick them because the other 2 combinations don't make sense. One of the combinations might say that at this level, we reject the null hypothesis and conclude that the data is not statistically significant. In other words, they say part of it right, but the other bit's wrong. And then the other one switches places. The first bit's wrong, but the second bit would be right. So these are the only 2 correct versions. If your p-value is less than the alpha, you reject the null hypothesis and conclude that the data is statistically significant. In English, that means I have proved that Scots people's IQ has increased. Right? It's more than 100 now. Used to be 100, but now I've proved it's bigger. And if that happened, I'd basically say there's no evidence here. I can't tell you if it was bigger or even less. Any questions so far? Okay, so let's do a couple of the early questions, which aren't hypothesis testing, but they're kind of theory, and we'll get those out the way first. Come in chat. Yeah, we got you. Gotcha. Oh, don't want the solution. Stop doing that. There we go. Maybe make it a little bit bigger if your screen's on the small side. Right, now, for the same sample data and the same null hypothesis, how does the p-value of a 2-tailed test compare to a 1-tailed test? Right, in a 2-tailed test, you're saying, is there evidence that it's not equal to, right, the number, right? It's different. And a 1-tailed test is, can you prove that it's bigger than, or can you prove that it's less than? Right, visually, can you imagine you've got your normal distribution, right? That goes like that. You're going to have 2 sides when it's not equal to, right? It could be bigger than, it could be less than. That makes it twice the size. So the p-value for a 2-tailed test is twice the p-value of a 1-tailed test. When you do the student t distribution, which of those formulas is the degrees of freedom? Haven't we talked about that one? It's n-1. Consider a test for the mean mu. If the p-value is such that we reject h0 at that level, can we assume that we'll also reject it at that level? So we got a p-value and we got evidence, right? We rejected the null hypothesis when it was 0.01. Does that mean we could reject it at the 0.05 level as well? What do you think the logic of that would be? So if you're less than 0.01, will you also be less than 0.05? Yeah. Right. If I'm smaller than 0.01, I'm definitely smaller than 0.05. I'm actually smaller than 0.02, 03, 04, 05, 6, 7, and 8 as well, right? And so that means, there we are, that answer. And that's that out the way. So we've done a little bit of theory, not much. So let's look at some stories. A random sample of 36 numbers is drawn from a mound-shaped and symmetric distribution. That's nice, right? So the population is normal. The sample mean is 12, and the standard deviation is 2. And we're going to use a significance level of 0.5. So that's my alpha. And we're going to conduct a 2-tailed test. And the 2-tailed test is for the claim that the population mean is 11.5. So the way they've phrased that is they've told us everything we need to know, but maybe not in a way that you would be 100% sure that you're on top of it. So let me start off. We need to know a null and alternate. In these questions, new is going to equal something. And the story, is it going to equal 11.5? And then there's going to be an alternate. And the alternate is bigger than that, less than that, or not equal to that. Right? That's always the three alternates. In this case, we're trying to prove well, they used the word two-tailed test. Two-tailed test is code that you're going to be doing a not equals to, right? It's got two sides to it. If they had said a one-tailed test, wouldn't that be either bigger than 11.5 or less than 11.5? And I would decide which of those made sense when I saw what the sample was, right? If the sample was 14, wouldn't I be proving it was bigger than 11.5? If the sample mean was 10, I'd be trying to prove that it's less than 11.5. But when they say it's a two-tailed always corresponds with a not equals to in hypothesis tests. So that's that guy. They have a significance level. If I read through the significance level, alpha is 0.05. So I got that guy. I'm ready to go. So I'm now going to, okay, where are you hiding? This is getting silly. I lost my window again. Right, I got it back. So we're going to put all of that information into SALT and eventually get the p-value, amongst other things. So here we go. Inferential statistics every time, one sample t every time. The mean in this case was 11.5. The standard deviation was 2. Oh, still 2. The random sample had 36 people in it, so that's 36. And we are trying to prove and I made a mistake here. The sample mean was 12, right? I have no idea what my windows are doing today. They're being really weird. See, I should be able to just click on that and see the fella. Is that it here? Right. Here we go. The sample mean was 12. The standard deviation was 2. There were 36 numbers. Double check. All done. We're being asked to compare it to 11.5 and to check, is there enough evidence to show that it's not 11.5? I'll generate the results, and here is all the numbers that we'll be using. So is it appropriate to use the student t distribution? Well, yes. How many degrees of freedom does it have? Although you can't see it, it's 35. Essentially, isn't it always one less than the sample size? So I didn't need to use SALT to do that. Now, what are the null and alternates? I've already set them up. It was equal to 11 and not equal to 11.5. So that makes it that one, right? Now, compute the sample statistic. It's this guy. You see that fellow there? The sample statistic is called the t-statistic in these questions. So I'll copy that. Put it in here. 3 decimal places. That's your answer. Now, the p-value that we have got is 0.14258. Do you see that guy right at the end? Now, in a normal, sensible question, wouldn't they just say p-value and you type the number in and round it off to 2 decimal places, right? For some reason, WebAssign has decided to make things a little bit awkward. So bear in mind what that number is, 0.14, right? 0.14. So it belongs in one of these categories. And the guy that's 0.14 is in this range. Does that make sense? Now, I'm only putting this out, I'm just making this up. Maybe they're doing this because there's some rounding off errors that can happen. And so if they wanted an exact value, you might type it in and then the last digit's wrong and it gives you its wrongs. So it's giving you some wiggle room here, isn't it? So that if you, you know, if something goes wrong, it's still fine. Are we good so far? Now, what's next? Well, based on that p-value, which I'm now going to have to put in so you can see it. So I'm just, the p-value that we had is this guy, right? I'm putting it up there so you can see it. Is this guy less than 0.05? Would you agree that's a definite no? Right? That is a no. And when it's a no, don't we have a choice of 4 sentences? When it's a no, don't you fail to reject the null hypothesis? So it's one of these two. And that it's not statistically significant. So my 2 sentences that I wrote, can you remember that was one of them? That's the sentence that you use when it's a no. If it was a different question, can you imagine that we got, I don't know, 0, 0, right? That guy. If it had been that guy, wouldn't we have said, oh yeah, we are rejecting our hypothesis and it's statistically significant? Wouldn't it be that sentence for a yes? In our question, it happens to be a no, so that's the sentence for a no, and then interprets the results. Well, since we're a no, there is insufficient evidence, right? And we're done. So from start to finish, we have a null alternate. We put all the information into SOLVE, and we will find the most important number we'll find is the p-value. And if the p-value is less than the significance level, we'll choose that as our conclusion. And if it is not less than the significance level, we'll pick that as our conclusion. So the next one, you are going to tell me, anybody who's in the medical field, if this is correct, because I have no ideas. Let X be a random variable that represents the pH of arterial plasma. Did you know, because I didn't, that your blood has an acidity? Is that right? Okay, so this isn't made up, this is real stuff, right? So the pH of your blood, I know 7 is neutral, right? So if you're acidic, aren't you typically bigger than 7?
It's usually kept between 7.3 and 7.4 with a little bit of wiggle room.
Right, so your body doesn't like a lot of movement in that acidity, right? So if you test acidity and it's an 8.6, you'd be really worried about that person, right? So what can make your blood go acidic? Is it a illness, or can you just, if you drink too much, does your acidity go up? I mean, what things make acidity go up?
It's usually like illness related. Like you either have like some sort of infection or something's going on that makes you acidic.
So infections would show up as high pHs?
Yeah.
Would that also be connected to either your kidneys or your liver? Would they do
yeah,
pH
both
thing?
of those. Like if you get like pancreatitis, you can become acidic. If you have DKA, which is diabetic ketoacidosis, you're obviously acidic. There's a bunch of different things that can cause that.
So this is good stuff, right? So let's see what they have got in this story. So for healthy adults, the mean is about 7.4. Now you were saying that sounds about right? Yeah. So that's what it should be, right? So a new drug for arthritis is being developed. Now, you know, when they do drugs, they test, are they effective? But don't they also test, do they do side effects? So in this case, they believe that this drug, arthritis drug, is changing the pH of its patients. So what the worst thing in the world you want to do is to cure one disease, and then the side effect is to give somebody an even worse disease, right? So, you know, if this is true, then this drug would probably not make it to the market, right? The side effect of making acidic might not be good. You know, cost benefit analysis, isn't that what you're always doing in medicine? Okay, I'll give you this and it's going to help this illness, but it might have this bad side effect. But then don't you end up getting a pill for the side effect? So it's not such a big side effect. I know one of my family had an issue, and the drug that they gave them to fix, oh God, I'll say it's the thyroid, I'm not sure. But they gave her a drug to fix her thyroids, right? But one of the side effects is it could make you nauseous. So what she did is she took the drug for her thyroid, then she had to take a anti-nausea pill, so that side effect didn't become a problem. So you can get around it, right? I don't know if there's any drug you can take to get your acidity of your blood back. Maybe there is, maybe there's not. Anyway, continue with the story. However, it is thought that this drug will change the pH, so you need a test. And a random sample of 31 patients who had arthritis and took the drug for 3 months. So that's who your sample is. Let me tell you right now, one of the rules you need for any kind of hypothesis test is, shouldn't your data be big enough? When you did proportions, the test should have been NP bigger than 10, NP less than 10, but WebAssign said NP bigger than 5, right? That was your test. When you do means like this, there is no real everybody agrees number, but it's typically about 30. So as long as you've got 30 in your sample, you can, that's typically concerned, we would consider that reasonable. I don't think it's great, right? 3,000 is great, right? But, you know, we'll live with 30. But theoretically, you could have 10 and you could get data and you could come to a conclusion, but you should be really kind of, I'm not going to bet my house on, right? Kind of way of looking at it. So 31's fine. And they got a mean of 8.6, which is, from what the conversations I'm hearing, is that not really bad?
At best, you'd be in a coma.
Right, so that person came in a really bad way. Or the average was a really bad way. God, that drug is bad. And the standard deviation is 2.9 and the significance level is 5. So do you see all the numbers that we need are in the second half of the story, right? And then which kind of test do they want, right? Do they want a bigger than, less than, or not equal to? Based on what I can see, wouldn't you probably think they should just prove it's bigger than, 7.4? But when I read it, it says, use the significance to test the claim that the drug has changed the pH. Well, okay. So it doesn't change mean not equal to. So that's what we're going to be doing, and not equal to because of that. Right, significance level 0.05. The null is equal to 7.4, and the alternate is not equal to it. So that makes it this one. Me personally, if you saw that data, I would be more inclined to choose, do we even have the choice? Yeah. Wouldn't I be probably choosing that one? that there's evidence to show that it's definitely bigger than 7.4. But we pick what they tell us, so it goes there. And then you choose, yes, you can do it, the sample is big enough. And at this point, I should write these down when I forget. 31 patients, 8.6 for the mean, 2.9 for the standard deviation. We are ready to rock and roll. So bring this over. Inferential, one sample. The mean in this case was 8.6. The standard deviation was 2.9. And the sample size was 31. The hypothesis test was that 7.4, I think, wasn't it? Yeah. The average was 70.4, and we're trying to prove that it's not that, right? It's changed. So it's a not equals to. Are you comfortable about how these numbers and the not equals to, how we got them from this story, right? Where they were. These three numbers, aren't they always going to come from the sample? Isn't this number going to be what we think it was, what it should be, that kind of thing? And then this comes from, are we trying to prove that it's bigger than that number? Is it less than that number, or is it just different? And so when we generate the results, there you can see it. Null and alternate, that's good. There's the t statistic, and there is the p-value. Looking at that p-value, would you agree that's nice and small? At least it's smaller than 0.05, which is all it needs to be smaller than in this question. So I'll now return to here. The sample test statistic is the t statistic. That's what it's called in these ones. Yesterday's stuff, it was the z-score. Here it's the t-score. And it's that guy. And to 3 decimal places, I believe you round that guy up to 4. Now the p-value we got was 0.028. So one of these intervals is 0.028, and I believe it's that one, isn't it? 0.028. It's in that range. Now, when they ask you to sketch it, these sketches are dead easy because there's only, it depends on the story. If it's a, I don't know if you can see that, but if it's a two-tailed test, you see a bit of shading on both sides. If you're trying to prove it's less than, it's only shaded on the left. If you want to prove it's bigger than, it's shaded on the right, and you're never going to use that shape. Right? So it's either going to be shaded on the outsides, shaded on the left, shaded on the right. If it's shaded on both sides, that's a not equal to. If it's shaded on the left, you're trying to prove it's less than. And if it's shaded on the right, you're trying to prove it's greater than. So every one of those picture questions isn't it going to look like that? Right. In our case, that one. Now, our test statistic was 0.028. And 0.028 is less than 0.5. So wouldn't that be a yes one? And so we go and we reject it, and it's statistically significant. And there is sufficient evidence to conclude that this drug has changed the mean pH. I'm kind of interested in things, and it's the way my mind works. So just so I can get it out of my head, if someone does have a really high acidic blood, is there a drug that you give them that just reduces it? Or is that not the way this works?
It's a little more complicated than that. You have to give them like a concoction of different things to help. So like you're giving them fluids, you're giving them medication, you're giving them other medication, you're doing a bunch of other things to like it's like a control thing. It's like a bunch of things happening to make it all happen at once.
I got
Like you can't do it quickly either.
Ooh, so That's not good. So if it's really high acid, I can imagine if you just put, is it plasma into the blood, basically dilute the blood. If you dilute the blood, the pH will go down, won't it? Because there's more fluid for the same amount of acidity.
You usually would never just be giving plasma. Like plasma, to give plasma is like a different kind of story. Like you'd be giving plasma in like a trauma situation. For that, you just be giving them saline, because saline will help thin out the blood. And it'll
So
help thin out the acidity.
saline is a better way of doing that, right?
Yeah, yeah. So there's
Plasma is
like,
because you've lost blood. And
yeah, so
saline-
plasma, well, plasma is because you want somebody to clot. So if they're like bleeding out somewhere, you give them plasma to help clot, like they're help their own blood clot quicker, so they stop just bleeding.
Interesting.
Yeah.
Good. Yeah. I hope never to have a high acidic rate and find out what you're talking about, because Brandon said if I'm an 8.4, I'm unconscious. So I don't want that number.
Yeah, it's not a good situation. Like we've had people come in pretty high, almost unconscious, but like barely there, and it's never a good sign. So I
No.
hope you don't.
I agree. I'm not.
Anything over, I think it's like 7.8 or 7.9 is where you start to get into coma territory.
Yeah, it gets pretty sketchy.
Yeah. Well, for the non-medical people, then that might not have been interesting, but for me it was. I enjoyed. I like learning stuff. That's the end of that question. Now you know it's got a kind of here's a story. Set up the null alternate. Get the numbers that you need so you can use salt. Find the p-value. If the p-value is less than alpha, you've got a yes. You've got the evidence you want. If the p-value is not less than alpha, you've got a no, insignificant. That's kind of the way the story goes. So, any questions so far? Okay. In a lot of ways, isn't this very much same old, same old? Isn't it very similar to the single proportion stuff, right? The theme of hypothesis testing really doesn't change too much. Okay, so next story, I'm going to talk about it, and that way I can write some stuff down. In this one, it's a version of question 6, which is to do with some coyotes, and a random sample of 46 coyotes. And they're in the region of northern Minnesota. And the average age of those coyotes is 2.05 years. I have no idea how you know how old a coyote is. It's not like you cut their head off and count the rings, but whatever it is, they know the age of it. We'll take the word for it. Well, I guess you could do it. They get born in seasons, don't things get born in the spring, and maybe you could do it that way. The standard deviation of the sample is 0.84. That you get from the sample, so I know what they would do there. Now, it used to be thought, so mu is the population, should be 1.7. So maybe in the past they've done similar things, and for a typical wolf pack, the average age of the wolves is 1.75. So evidently wolves don't last many seasons, right? Must be a tough life being a wolf. And we're going to do a significance level of 0.01. And we're being asked, does this sample indicate that they live longer than the average, right? So we're trying to prove, is the average greater than 1.75, right? And superficially, would you agree it looks like they live a little bit longer? The average used to be this particular group, they live a bit longer. It's a good sign. So all the numbers we want are here. And so I can, if salt wants to be my friend, here we go. At this point, really salt takes over. So here we go. Over here. Sample size was 46 coyotes. Not a great sample, but it'll work. It's bigger than 30. the mean of the sample was 2 and a bit years, and I put the 46 in the wrong place. That's the sample size. That's the mean, and that's the standard deviation. So there, now in the right order. The mean was 2 and a bit, the standard deviation was 0.8, and the sample size was 46. Our hypothesis test is that it used to be 1.75, and we're trying to prove it's greater than. Are you comfortable how those come from the sample and this comes from the hypothesis? So we're going to calculate in a few minutes, a few seconds, the p-value, and we should be able to then compare it to the significance level, which is 0.01 this time, right? That's what they told us to use. So when I generate the results here, the p-value is this guy here. You see it? 0.009757. Okay. So let's fill in the story. Significance level 0.01. The null is it's equal to 1.75, and we're trying to prove it's bigger than. So it's this one. Yes, we can do it. It's large enough. There we go. The test statistic happens to be 2.422. The p-value that we got was 0.009 and change. So 0.009 and change, isn't it that one? Right, 0.009 is less than 0.10. It's a less than story, so which one of them has got a shading to the left? It's that one. The guy that we got is less than the significance level. That means we have a yes. Right? And in a yes, we reject it, and it's statistically significant. And if it's a yes, there is sufficient evidence that these wolves live longer than the other ones. And I would assume that if the wolves live longer, it probably means that they're doing okay, right? That they're living a bit longer, they're getting enough food, right? Things are going well for that wolf. If we had a situation where the wolves were, the average life of the wolf was a lot less than 1.75, wouldn't that be an indication that there's a problem, right? There's not enough food or too many wolves or whatever it is. So I guess you could use that information to decide how healthy, in this case, a wolf population is. Useless piece of information, but I like telling you stuff. Scotland used to have wolves. They are now extinct. I think the last wolf in Scotland was killed in the late 1700s. So we had a European wolf and now we don't. And the reason I know this is because I saw a documentary where an idiot, in my opinion, decided that he wanted to reintroduce wolves back into the Highlands. And he had some wolves, and he had the wolf pack. Obviously, that's what you do. Wolves go about in a pack. And he had them in a big cage fence thing. And his goal was to, because they were zoo wolves, right? They didn't know how to fend for themselves outside of, a zoo. His goal was to reintroduce them to the wild. And the reason I'm calling the guy an idiot, do you really want wolves wandering around where people are? I get this feeling that wolves eat people, or packs of them do. I would not feel comfortable about doing hiking in the mountains in Scotland if I knew there were a pack of wolves around. Because unlike in America, nobody has guns. So using harsh words against wolves probably wouldn't be a success. And I know I can't outrun them. And I probably would taste quite good. So none of those make me feel comfortable about that. So, useless piece of information. He wasn't allowed to do it, by the way. For obvious reasons, they told him it wasn't safe. But it was an interesting, I wish I could remember the name of it. He actually lived with the wolves. He slept in the enclosure with them, and he became one of the pack. He was a real weird looking guy.
There was a movie like that called Grizzly Man, where the guy slept with grizzly bears and they ended up eating him at the end of the movie. Well, yeah, play stupid games, get stupid prizes, right?
Yeah,
Exactly.
when they give out stupid prizes. What's that called? The Darwin Awards, where you give prizes to people who are leaving the gene pool.
Yep.
I think some people probably. I don't want anybody to die, but there are some people who probably shouldn't have children for all sorts of reasons. Like sleeping with wolves would be one of them. Okay, today we're going to finish a little bit early, so I want to just do this last question. I've got some things to do, and we're ahead of the schedule, so I'm not too worried about that. And I'll talk, once I'm finished, a little bit about the final that's coming up. So for the last one of today, do I want the trout one? Nah, I don't want the trout one. That's pretty straightforward. Okay, question 8. Socially conscious investors screen out stocks of alcohol and tobacco. Right, so they don't invest in what they considered antisocial ways of making money, right? Fair enough, that's your money, do what you want. Or they have poor labour practices like, I can't remember who it is. Who's the guy that makes shoes and they're almost always made in China with slave labour? Is that Nika?
All of them.
All of them, right? So they wouldn't invest in them, allegedly. Although, who knows? Now, some examples of good socially conscious companies are Johnston & Johnston, Dell Computers, Bank of America, and Home Depot. I wonder how much money he got for mentioning those, right? Product placement. The question is, are these stocks overpriced? Now, one way to measure the value of a stock is P to E. I think that's price to earnings. So the price of the stock divided by how much per stock that company earns. So it's P to E. High P to E ratios can indicate that a stock is overpriced. It can also mean that that stock is liked, right? People like certain stocks because they feel it's a good company, it's not going to go bankrupt on me. For the S&P stock index of all the major stocks, the typical PE to ratio is 19.4. So that is the status quo, right? A typical stock is 19.4 PE. If you have a stock it's bigger than that, you might be buying an overpriced stock. If you get one under that, you might be buying an under stock. So a random sample of 36 socially conscious stocks. So they've now told me that the sample is 36. And they've told me that the mean P to E of them is 17.7 and that the standard deviation is 5.4. Would you agree that line there basically tells me the major numbers I need? Now, does this indicate, so this is the bit we're going to do, that the average P to E ratio of socially conscious stocks is, and the key words here are, is different or is different either way. Does it not make it a not equal to story? Is it different either way? And we're going to do it at a significance level of 0.05. So there's 0.05. The one that we're looking for is this one. It's always equal for the null, and in this case, not equal to does the other, and sample size is large enough. And at this point, salt takes over. So for this stock, it's 17.7. The standard deviation was 5.4, and there were 36 in the sample. And we are going to do a comparison with what it typically should be, which is 19.4. And we're trying to test, is it different? So you're comfortable about these three came from the sample, and this is the comparison. Right. Every story has data from the sample and something you're trying to compare it against. So I'll generate the results, and here is our p-value, amongst other things. So the test statistic, which you can't see anymore, but I'm copying it, is -1.8 and change. To 3 decimal places, that becomes a 9. The p-value, which again you cannot see, is 0.06. So 0.06 is in that range. Agreed? The third one. Right, 0.06 is somewhere between here and here. This is a not equals to one, so don't we click on the two shadeds? And we are comparing that to a 0.05. Well, a 0.06 is not less than a 0.05. So that's a no. And a no is this one. Fail to reject a null, not statistically significant. A no is there is insufficient level to show that these stocks differ from the stock exchange. So if you were that kind of investor, the evidence, statistical evidence is that you're not going to make or lose any more money than picking any other stock, right? They're not dangerous, overpriced, they're not under. At least we can't prove that they are. Based on the raw data, of course, if I looked at it, I would say if there was any evidence going to pop up, wouldn't it be that these are less than the typical average PTE? Which would mean, if this was true, that that would be a pretty safe investment. Right, so that's us for today. We're about halfway through roughly. Couple of things to mention, and then while I'm doing that, you can all say your last name. Let's get back to the main screen. Here we go. This is week 5 finished. There's 2 weeks to go. Actually, a little bit less than 2 weeks. 1 week on this Thursday coming is the final. So I would suggest really strongly that you think about getting some extra time somewhere. And I know that can be difficult, but you really need to get ready for your final. So start looking over week 1, 2, 3 stuff, because your final is going to be comprehensive, right? It's going to contain stuff from everywhere, and you want to be, ready for it as much as you can. So that's my first piece of suggestion: start revising.
Is
Get
the
ready
final
for it.
gonna be like the midterm where like you open note and stuff still, or no?
Yeah, still the same. You're going to have it in 2 parts. The stuff that's in WebAssign would be like the stuff we did today, because
Okay.
there's a salt button and you need to use salt.
Okay.
And then the other half will be questions like things like probability, where you don't need salt, and those would belong in there.
Okay.
And it's 30% of your grade. Now that's enough to make you or break you, right? So if your grade's not great, it can help you a lot. If you put the work in and you do well. If your grade's great and you don't do anything, then the opposite is true. So we don't want the opposite, right? We want to make sure that you keep your grade high and improve it if you can. This week, usual, your test is already online, so you'll be able to do it whenever you feel like it. Got to be done by Sunday. Extensions are still going if you need them, but remember you lose a bonus point, 1% on your homework every time you do that. And so you don't want to, if you didn't do it at all, your homework grade is going to be theoretically 107%. Can you imagine that extra 7% can make a big difference? So it's good to do your homework on time anyway, but that's just a little incentive. But if things get to, sometimes things get on top of you, ask for an extension, that's fine. Just send it to my email address. Don't use any WebAssign links, I don't see them. That's about it for today, so we're finishing a little bit early. I will see you on Monday. What's that, bright-eyed and bushy-tailed? Do you use that phrase, or is that a British phrase?
No, use that phrase.
Okay, so I don't know where it came from, probably a book.
Question.
Yes.
So I know the
Lost you.
is that just for the WebAssign, or is that for both of the parts?
You really only need it for WebAssign. I don't think WebAssign would help you with the questions that you do by hand.
Oh, I meant our last exam. Like, I know the part it's graded for the WebAssign portion. I was wondering if the other part of the exam, like the written part, if that was graded yet, or if that was incorporated in that grade.
It's incorporated. So if you go online to Canvas, you'll actually see the solutions to the paper version, I guess I'll call it, right? The written down stuff. And if you go to WebAssign, you'll be able to see how you did in that as well, because that's now, it should be visible, I believe it is.
Okay, thank you.
Right. So bye-bye. I'll hang about for any questions and I'll see you on Monday otherwise.